In one of the driest industrial landscapes on Earth, Australia is building a factory designed to feed farms with gas. Not power them, not heat them, feed them. On the coast of Western Australia, more than 100 steel modules are being assembled into Project Ceres, a urea plant expected to produce about 2.3 million tonnes of fertilizer every year. Its price is now commonly placed near 6.5 billion Australian dollars. Its largest pieces have crossed an ocean. Its future gas supply has been locked in for 20 years. And when the plant is complete, a long enclosed conveyor will carry its product straight to the Port of Dampier. At first, this sounds like an easy story about national self-reliance. Australia has recently imported roughly 2.4 million tonnes of urea in a year, while this one plant is designed to make almost the same amount. But those two numbers hide the real story. Project Ceres is also designed as Australia's first dedicated urea export project. It will consume fossil gas on an industrial scale, and it is rising on Murujuga, a living cultural landscape inscribed on UNESCO's World Heritage List in 2025, after more than 50,000 years of care by its traditional owners and custodians. So this is not just a giant factory, it is a collision between food security, export ambition, fossil fuel chemistry, extreme construction, and irreplaceable cultural heritage. And the engineering question is only the beginning. Can Australia gain the benefits of this plant without paying a price that cannot be reversed? To understand why anyone would build a fertilizer plant here, start with the ingredient that matters most: natural gas. If you enjoy mega projects where the impressive numbers are only the surface, subscribe to Mega Projects. Because the process inside this plant is stranger than the building outside it. Project Ceres sits roughly 20 kilometres northwest of Karratha, close to the gas industry of the Pilbara and the deep water export infrastructure at Dampier. Woodside has agreed to supply approximately 130 terajoules of gas every day for 20 years, with supply expected to come primarily from the Scarborough project. That is not merely fuel for a power station. The methane in the gas becomes the raw material for nitrogen fertilizer. Australia's dependence on imported urea became especially visible when international supply chains tightened and fertilizer prices surged. Urea is used across broadacre farming, horticulture, and other industries. If imports become expensive or unreliable, the pressure moves quickly through farm budgets and eventually into the food system. Project Ceres therefore promises something strategically valuable: a very large source of urea made inside Australia, with an offtake agreement involving Incitec pivot and access to both domestic and export markets. But capacity is not the same as a guarantee that every tonne will remain in Australia. The project has been financed partly around exports, and its port connection is central to the design. The honest claim is not that one factory makes Australia independent overnight. It is that the factory creates a domestic production base large enough to change Australia's options. Urea may arrive on a farm as small white granules, but it begins with molecules pulled from gas, air, and water. First, the plant must separate hydrogen from methane. Natural gas is cleaned so sulfur does not poison the catalysts. Then combined with steam and oxygen inside an autothermal reformer. The chemistry creates synthesis gas, mainly hydrogen, carbon monoxide, and carbon dioxide. The carbon monoxide is reacted with more steam to make additional hydrogen and carbon dioxide. After the carbon dioxide is removed, nitrogen from the air is added. Hydrogen and nitrogen are then compressed and passed over a catalyst, producing ammonia. That ammonia is only the halfway point. To make urea, ammonia is reacted with carbon dioxide under high pressure. The intermediate compounds are converted into a concentrated urea melt. In the finishing section, droplets of that melt are sprayed onto tiny seed particles suspended in moving air. Layer by layer, the particles grow into hard granules that can survive storage, conveyors, and ocean transport. The clever circularity is that carbon dioxide separated during hydrogen production becomes a feedstock in the urea section. Instead of treating all of it as an immediate waste stream, the plant captures a large portion inside the product. But that does not make the fertilizer green. The hydrogen still comes from fossil gas. The site generates its own power, mainly with gas turbines, and the approved environmental assessment identifies substantial greenhouse emissions. This is a more efficient version of conventional gas-based urea production, not a renewable ammonia plant. That distinction matters because the most advanced part of Ceres is not what it makes. It is how engineers are trying to make so much of it in one continuous system. At the center of the ammonia plant is Topsoe's Syncor technology. Instead of the more familiar arrangement of a fired primary reformer followed by a secondary reformer, Syncor uses a single-step autothermal reformer. In simple terms, part of the gas reacts with oxygen inside the vessel and supplies the heat needed for the rest of the process. Topsoe says the configuration can reduce steam throughput by about 80% compared with conventional reforming. That reduction has consequences far beyond the reformer. Less steam means smaller steam systems, lower water demand, and less equipment moving enormous quantities of hot vapor around the plant. On a site where fresh water must ultimately be produced from seawater, saving steam is especially valuable. The ammonia line is designed for approximately 3,500 tons per day. Topsoe describes the planned unit as the world's largest single-line ammonia plant. The urea side is designed for around 6,200 tons of granulated product per day. It uses Snam-Progetti urea technology, including reactor internals developed to improve mixing and conversion while reducing energy demand. The final plant is not one heroic machine, but a chain of reactors, compressors, heat exchangers, columns, tanks, pumps, and control systems. If one critical link stops, production across the chain can stop with it. The same logic explains the enormous storage and handling system. Urea does not leave the reactor ready for a ship. It must be granulated, cooled, screened, coated, stored, and then moved without absorbing too much moisture or breaking into dust. Chemistry creates the product. Reliability creates the business. And building that reliable chain on a remote peninsula required the project team to turn the factory itself into cargo. Project Ceres is being assembled from 110 prefabricated modules, 47 pre-assembled units, and 63 pipe rack structures, with a combined mass of about 62,885 tons. Many were fabricated at Larsen and Toubro's Kattopali yard near Chennai, where pipes, platforms, equipment, and structural steel could be installed in a controlled industrial environment. While foundations and underground services advanced in Western Australia, entire sections of the process plant took shape in India. Then came the difficult part, moving them. The modules travelled by sea to Dampier, were transferred onto multi-axle transporters and carried along a carefully prepared route to the construction site. One of the most striking pieces arrived in 2025. It measured 42 metres long, 42 metres high, and 14.7 metres wide, yet it came ashore as a single 985-ton assembly. Imagine transporting a 14-storey steel building that cannot bend, cannot scrape a bridge, and cannot arrive with its pipe connections out of alignment. Modular construction reduces the amount of complex work performed at the remote site, but it does not remove risk. It moves that risk into fabrication tolerances, sea fastening, heavy transport, and final connection. Every flange, cable route, and support must meet the equipment already waiting in Karratha. The scale continues inside the completed plant. Saipem lists more than 111,000 cubic meters of concrete, over 46,000 tons of fabricated steel structures, more than 10,000 tons of piping, and approximately 3,223 kilometers of electrical, instrument, and communications cable. That cable length is roughly the distance from Karratha to Adelaide. Yet almost all of it will be packed into one industrial complex, carrying power and thousands of signals that tell operators whether the chemistry is behaving. The factory also needs an ecosystem beyond its process modules. Project Ceres occupies two main areas connected by a causeway. It requires cooling water, desalinated process water, electrical generation, storage, roads, and a route to the port. The approved design allows 101 megawatts of gas-fired generation and 5 megawatts of installed solar power. A future connection to a proposed 50-megawatt traditional owner-owned solar farm is being explored, but it is not yet the plant's main energy source. Water Corporation is expanding common user seawater supply and brine disposal infrastructure. At the other end of the production line, finished granules will enter a storage shed with a capacity of about 75,000 tons. From there, an enclosed conveyor of more than 3 kilometers will move urea toward the port, where the approved bulk handling rate reaches 2,200 tons per hour. The enclosure is practical environmental engineering. It limits product loss and helps control fertilizer dust during the journey to the ship loader. Public finance is woven into this private industrial project. The Northern Australia Infrastructure Facility committed loans of up to 220 million Australian dollars to the plant, 95 million to water infrastructure, and 160 million to the port expansion. Export Finance Australia also announced a $269 million loan, while the Western Australian Government funded supporting roads and regional works. Supporters see a new manufacturing industry, construction jobs, permanent operating roles, and value added to Australian gas before export. They also see a plant capable of supplying local agriculture while competing in Asia-Pacific markets. Critics see public money and long-term gas consumption committed to heavy industry in one of Australia's most sensitive cultural landscapes. That is where the story stops being a contest of engineering numbers. Murujuga is not an empty industrial desert. It includes the Burrup Peninsula, islands, surrounding waters, and submerged landscapes. UNESCO describes it as a living cultural landscape shaped by the law and by more than 50,000 years of care by the Ngada Ngali. Its rock art is not simply a collection of old pictures. The petroglyphs, stone structures, stories, spiritual knowledge, and continuing cultural practices form one connected system. UNESCO calls the assemblage one of the vastest and densest known concentrations of petroglyphs in the world. Industry was already operating on Murujuga long before Project Ceres. The concern is cumulative. Nitrogen oxides, sulfur compounds, dust, and other emissions from multiple sources may alter the chemistry around exposed rock surfaces over long periods. When Western Australia's Environmental Protection Authority assessed the urea project, it acknowledged that there was no full scientific consensus about the residual cumulative impact on the rock art. It recommended a cautious condition. Emissions from the project must not accelerate weathering beyond natural rates. The project was approved with monitoring and management requirements. The Murujuga Aboriginal Corporation supported agreements and heritage management measures, while other traditional owners and campaigners opposed disturbance and argued that consent was not unanimous. Under the approved heritage arrangements, some cultural material within the footprint was designated for careful relocation, while other material was to be protected in place. Then, in 2025, the wider Murujuga cultural landscape received World Heritage status, and the federal government issued a separate partial declaration protecting specified areas under Indigenous heritage law. Approval, therefore, did not erase the conflict. It raised the standard by which the plant will be judged. A successful startup will prove the machinery works. Decades of credible monitoring will be needed to show whether the protection system works too. By early January 2026, Perdaman reported overall progress at 66%, with engineering and procurement largely complete, but substantial construction still ahead. Saipem and Clough now point to completion in 2027. If Ceres reaches full output, the numbers will be extraordinary. Roughly 2.3 million tonnes of urea each year is close to Australia's recent annual import volume. A single ammonia line will run at a scale rarely attempted. Ships will carry granules made from Pilbara gas to farms in Australia and overseas. But the project's real verdict cannot be reduced to tonnes. For supply security, the important question is, How much product is reliably available to Australian users when global markets tighten? For climate, the question is whether efficiency gains are followed by deeper decarbonisation, rather than used to disguise a long-lived fossil gas dependence. For Murujuga, the question is whether promised monitoring can detect harm early enough to prevent it, not merely document it afterward. That makes Project Ceres a very modern mega-project. It is technically sophisticated, economically ambitious, and impossible to separate from the place beneath it. The steel modules may be the most visible achievement. The chemistry may be the cleverest. Yet the hardest engineering task is one no reactor can solve: balancing a factory designed for decades of operation with a cultural landscape measured in tens of thousands of years. If the plant works perfectly, but its protections fail, Australia will not be able to manufacture a replacement for what was lost. That is the standard Ceres must meet. For more stories about the technology, trade-offs, and consequences behind the world's largest builds, subscribe to Mega Projects. And tell us in the comments, which test should matter most here? Reliable domestic supply, lower carbon intensity, or measurable protection of Murujuga?